All right, moving along, I wanted to just remind everyone about the basic steps in hypothesis testing. So we just went through a hypothesis test, and hopefully those basic steps were pretty apparent there. But again, you're learning about a lot of new terms and ideas in chapters 22 and 23. And I tried to highlight some of the main ideas here, or the main concepts that are going to be important to understand. So you always start with your null and alternative hypothesis. We then collect some data. We summarize the data in the form of a statistic. We call this statistic or let me backtrack. So we gather some data, we collect some data, we summarize the data in the form of a sample statistic, so either a sample mean or a sample proportion, and then we have to convert that sample statistic to a z-score. And within the context of hypothesis testing, remember, we call that a test statistic. So if we ever ask you to compute a test statistic, we essentially want you to take your sample statistic and convert it to a z-score. Once we have the test statistic, we can use table B to find what's called a p-value. The p-value helps us determine how unlikely our result would be if we assume the null is true. So remember, we start a hypothesis test assuming the null is true, and we're trying to see if our results are likely or unlikely under that assumption. And then we reach a conclusion. So we reach a conclusion about the null. We're either going to reject it or we're not going to reject it. And we make that decision by comparing our p-value to a significance level, or sometimes we call that an alpha level. So most times, actually, we refer to the significance level as an alpha level. But we want you to know these mean the same thing. Also remember that how you compute your test statistic is going to be a little bit different depending on whether you have means or proportions. So that's why it's really going to be important at the outset for you to know what kind of data you're working with. Do you have means or do you have proportions? I've seen a lot of cases where a student might work through a problem and they're trying to fit the information into the proportion formula when actually they don't have proportions, they have means, or vice versa. So we want you to know right away what you have and to be able to pick out the relevant information and fit it or insert it into the right formula. So remember, we can have either proportions or means, and in both cases we're computing a z, and the general format is the same. So we're taking our sample statistic minus the claimed population parameter, that's what's in our numerator, and then the denominator would be what we're estimating the standard deviation of our sampling distribution to be. So we have an observation minus a claimed value divided by a standard deviation. So the format is very, very similar, the general format, but the pieces are going to be a little bit different depending on whether you're dealing with proportions or means. So, and again, we're going to practice this in a little while. I have an example coming up with proportions, one coming up with means. So we're going to, again, get lots of practice. Here is an example. Speaking of examples, I thought this was kind of interesting. Now, before I show you some information, I want you to think about Thanksgiving and pie. I'm sure many of you have a favorite pie. Imagine that favorite pie in your head right now. What do you think the most popular favorite Thanksgiving pie is? Maybe write that down. We'll see if you're right. So some researchers were interested in this. They asked people what their favorite Thanksgiving pies were, and they came up with a claim about what the most favorite Thanksgiving pie is. Okay, so here is appropriately, here's a pie chart with some pies. So, and maybe look to see, is this an appropriate way of using a pie chart? So think back to chapter 10. You'll notice that pumpkin is the most popular. I was a little sad here. I kind of probably fall into the other category. My favorite pie is coconut cream, and it's not here. Maybe that's not a good Thanksgiving pie, I'm not sure. But these researchers claim that, a lot of people like pumpkin pie for Thanksgiving. That's a favorite staple of Thanksgiving. Let's use this information to conduct a hypothesis test. Okay, so let's say it's claimed that 36% of Americans prefer pumpkin pie as a dessert on Thanksgiving. But you believe this percentage is too low. So you survey a random sample of 350 individuals, and you find that 137 of them actually prefer pumpkin pie. So use this information to conduct a hypothesis test with alpha equals 0.05. So one thing I encourage you to do with some of these examples is maybe just pause, try to do it yourself, and then come back and see if your results match mine, just as a way of testing yourself. If you're not sure how to do it, that's okay. You can hang around here and I'll help you, I'll show you. But let's see what we have in the problem. So again, let's start from the beginning. We have a claim about a population parameter. Here we have a claim about a population proportion. So I'm going to take 36 and turn it into a proportion. So P equals 0.36. I'm then going to look at some of the other information that I have here. So I think the actual percentage is too low, or excuse me, I believe the claimed percentage is too low. So I actually think something higher than 36% is what's really going on. So again, look for those keywords to help you figure out what your alternative hypothesis should be. I'm then going to survey some people. Now I survey 350 people, and 137 of those 350 respond that they like pumpkin pie. So to find my sample proportion here, I need to take 137 and divide it by 350. So sometimes we might actually just give you that sample proportion. Other times we're going to give you the information that you need to calculate that. So we'll give you the sample size, and then we'll give you the number that fall into a certain category. And so here, this is going to end up being 0.39. So I have p hat, I have n, I have p. I'm all set to go. Let's do this hypothesis test. So again, what are our hypotheses going to be? P equals 0.36, p greater than 0.36. Hopefully this is matching what you're thinking about in terms of how to solve the problem. I'm gonna leave out a few things here, but if you're not sure how I'm getting certain numbers, please ask me and I'll let you know. But I'm just plugging things into my formula for proportions, my test statistic formula for proportions. And again, when I figured this out, I rounded a bit along the way, so I got approximately 1.0 as my test statistic. If you got something a little different, that's okay, as long as it's close to 1 and you obviously were plugging things in the right way into the formula. If you're getting something way different from 1, let me know so I can try to identify maybe what's going wrong. So I have 1. Now I'm going to go to table B. I'm going to look up 1. So I'm going to leave this part out, but I want you to see if you know how I got this number. So I go to table B, and in the end, here's what my p-value ends up being, 0.1587. So this is after I went to table B, I took the percentile from table B, I subtracted it from 100 since I have the greater than sign in my alternative. And then I divided the result by 100 to turn it into a probability. I will fail to reject the null. And that's because my p-value is greater than alpha. So this is kind of shorthand for stating our conclusion. But I'm not finding evidence with my sample that the population proportion is something greater or something. The claim is that the true percentage in the population is 36%. I'm not finding evidence against that claim. That doesn't mean that claim is true. It just means that with my sample, I'm not seeing enough evidence against that original claim. So I can't reject that original claim. So I'm failing to reject the null. And again, it's because my p-value ends up being larger than the alpha level. Okay, so do we have enough time? I think we have enough time for a couple more things, and then we'll stop this video. Again, ask me questions. If any of this is not making sense, or if your numbers are really different, let me know. Hopefully I didn't make a calculation error, but it's always possible. Remember, this is just a quick review of decision rules, so this is going to be important. When you conduct a hypothesis test, remember, and I've said this already in this lecture so far, but if the p-value is less than or equal to the alpha level, the decision is to reject the null hypothesis. If it's greater than the alpha level, the decision is to fail to reject or not reject. So notice here that we're being really careful in our language. We're not saying we think the null is true. We're not saying we accept the null or the null is false. We're just saying we reject or we do not reject. We reject or we fail to reject. So it's really important how you use language when you're stating your conclusions. And just another thing related to this idea of the conclusion. So we always begin a hypothesis test by assuming the null is true. And this, if you go back to the start of chapter 22, remember we made this analogy to a jury trial. You start a trial with the assumption that the defendant is innocent. So we then gather some information and we want to relate it back to that original claim. So all we can do is look at the information we have and see if that supports this original claim or if it does not support. So in a jury trial, remember we assume someone is innocent, we look at the information that we get during the trial, we analyze that information, and it might be such where it supports that the person is innocent. We don't come back and say that they're innocent, but we don't have enough information to conclude that they're guilty, that they did something. So we never can know if the null is really true or not. We can't conclude if it's true or false, but we do begin with this assumption that it's true. And that's important. I know that's kind of confusing. You might be thinking, well, we assume it's true, and then we get information and we can't reject it, so why can't we say then that it's true? Hopefully you're thinking about the fact that all you have is your one single sample. And your sample could be different from the random sample that somebody else obtains. And you're not sampling the whole population. So because of that, we just can't know for sure if that original claim is true or not. So we analyze our sample data, we determine a p-value, and the p-value tells us the probability of observing our sample data or more extreme data if the null is true. So it's not the probability that the null is true, it's just the probability of observing our sample results if we assume the null is true. So this might be actually a good place to pause, and then we'll come back and we'll pick up on these ideas and just talk a little bit more about what the p-value does tell us and what it does not tell us, and we'll work through lots more examples.